Have you ever really stopped to think about what's happening when you click on a link or send an email? I mean, under the hood, there's this hidden set of rules that's basically running the entire internet. Today, we're going to pull back that curtain and demystify it all by comparing two big models, the theoretical OSI model and the practical, everyday TCP IP model that is, actually powering your connection right this very second.
It really is a simple question, right? But the answer? Oh, it's this brilliant, layered system that makes global communication happen in like the blink of an eye. We use it every single day, but how does a request from your computer find its way to a server halfway across the planet and back again? Well, let's find out.
Okay, here is the absolute best way to think about this. The OSI model, it's like a super detailed theoretical map of every single road, street, and alleyway that could possibly exist. It's fantastic for learning the geography. But the TCP IP model, that's the GPS in your car. It's the practical tool that just gives you the most efficient route. It's the one everybody actually uses every single day. So let's get into this tale of two models. Because to really get it, you have to understand what each one was built for. One was basically designed for a classroom, and the other one was built for the real world. So first up, we've got OSI, which stands for Open Systems Interconnection. You should think of this as the perfect blueprint, drawn up by a committee of experts. It breaks down every little networking function into 7 distinct layers. And all that detail is incredibly useful if you're, say, a network engineer trying to figure out what went wrong. You can literally check it layer by layer. It is the gold standard for teaching the theory. And then there's TCP/IP. This is the workhorse. It's a much more streamlined 4-layer model, and it is the actual foundation of the internet we use. It's not just some idea. It's the real set of rules your phone, your laptop, even your smart fridge is using right now to be online. It's all about practicality over perfection. All right, so let's actually deconstruct the TCP/IP stack that's running, well, everything. We're going to follow the journey of your data from the app you click on all the way down to the physical Wi-Fi signals and cables. Okay, so starting from the top where you are, we have layer 4, the application layer. This is your web browser, your email app, the stuff you actually see and touch. When you click send, that data moves down to layer 3, the transport layer. This guy is like the traffic cop. It chooses between TCP for a reliable tracked package delivery or UDP for pure speed, kind of like sending a postcard. Next, your data hits layer 2, the internet layer. Think of this as the global postal service. It stamps your data with an IP address so it knows where to go. And finally, it all lands at layer 1, the network access layer. This is the physical stuff, the Wi-Fi waves, the Ethernet cable that actually sends the ones and zeros. That's the whole journey down the stack, from your app to the actual wire. So you've got to ask, right? If the 7-layer OSI model is so detailed and perfect, why did the simpler 4-layer TCP/IP model become the undisputed king of the internet? Well, the answer really comes down to timing and history. See, TCP/IP was built by DARPA right alongside ARPANET, which was the internet's granddaddy. It was built by developers, for developers, and it was tested in the real world as the network grew. It just worked, and it was there first. So after all that theory, after all the talk of 7 conceptual layers, how many do we actually use to run the entire global internet? Just 4. Yep, that's it. 4 practical, battle-tested layers that just plain get the job done. Now this is where it gets really cool, seeing how we get from 7 layers down to 4. TCP/IP didn't just throw the other layers out, it bundled them up logically. Just look at this. OSI's top 3 layers, application, presentation, and session, they all get combined into TCP/IP's single, powerful application layer. And then down at the bottom, the physical and data link layers get merged into the network access layer. It's a perfect picture of how they streamlined everything for the real world. Okay, theory is great and all, but let's make this real. For this next part, we're going to do a little mini-lab. We'll use a few simple commands to actually find evidence of these TCP/IP layers working on your computer right now. We're going to climb back up the stack from the hardware all the way to the software. So we're starting at the very bottom, layer 1, the network access layer. This is your physical hardware, and every single piece has its own unique burned-in address. Let's go find yours. On a Windows machine, just open up the command prompt and type this really simple command, get MAC. This is basically asking your computer, hey, what's the unique serial number for my network card? And what pops up? That's your MAC address. Now, this isn't your internet address. It's more like your device's physical fingerprint. It's used to talk to other devices right there on your local network, like your Wi-Fi router. And just like that, you've confirmed it. The network access layer, layer 1, is up and running.
Awesome. Now, let's move one level up to layer 2, the internet layer. This is where your logical address lives, the one that lets you cruise around the entire internet.
To find this one, the command you want is ipconfig. This is one of the most fundamental networking commands out there, and it gives you a quick snapshot of your computer's identity on the network.
The output shows a few things, but what you're looking for is the IPv4 address. That's your current address online. You'll also see something called a default gateway, which is just your router's address, the door from your house to the giant street that is the internet. And there you have it. Layer 2, the internet layer, is doing its job.
All right, let's keep climbing. We're now at layer 3, the transport layer. This is the layer that manages all the different conversations your computer is having at the exact same time. Let's go take a peek at that switchboard. The command for this one is netstat-an. Think of this like asking your computer to show you a list of all its active phone calls and all the lines that are open and waiting for one.
Okay, you're going to see a long list of active TCP and UDP connections. See where your IP address is followed by a colon and then a number. That number is the port. This command is giving you direct proof that layer 3 is managing all those different connections for all your different apps. Pretty cool, right?
And finally, we've made it to the top. Layer 4, the application layer. One of its most critical jobs is translating the human-friendly website names we use into the numeric IP addresses that computers understand. That whole process is called DNS.
We can test this directly with a command called nslookup, and then just follow it with any website. Let's use www.google.com. This is just like looking up a name in the internet's giant address book. And boom, what you'll get back is the official server name and, more importantly, the IP addresses for it. You just used the DNS protocol to turn a name into a number, a perfect, tangible example of the application layer making the internet usable for all of us.
So, there you have it. We journeyed from a theoretical 7-layer map all the way to the practical 4-layer GPS that runs our entire digital world, and we even found proof of it on our own machines. So the next time you're browsing the web, just remember that stack. Your computer is having thousands of tiny, layered conversations every single second. Now you have the tools to listen in. What do you think it's saying?